Okay, I think we'll get going. This is Design at Large. I'm Jim Holland, and it's my great pleasure to introduce Maneesh Agrawala from Stanford. He's recently moved from Berkeley to Stanford. He got his degree at Stanford with Pat Hanrahan, who led off this quarter's Design at Large sequence. We had Jeff Faire here, who's one of Maneesh's students. So it's totally inbred, and we embrace that. With all really great folks. Manish works in so many areas. You know, he's well known surely in computer graphics. You know, he's well known in human-computer interaction. He's surely also one of the leaders of information visualization. He's the director of the Brown Institute for
Media.
Don't tell me, I've got it. Brown Institute for Media Innovation.
Very good.
It's joint between Stanford and Columbia. Today he's going to tell us a story. And one of the things that I think is so wonderful about Maneesh is he often not only does some really interesting work in areas, but he builds tools to help others do similar kinds of work. I was most impressed by Maneesh's PhD thesis, where he looked at how people draw maps. And we as people, if you were going to invite me over to your house in the evening for dinner, you would maybe sketch a map on the back of an envelope, and that map would have all kinds of regularizations. It wouldn't be to scale. It would have debugging information in it. And Maneesh looked at that and built these great algorithms to draw those kind of maps. So I'm going to stop and let him tell us a story.
Great, thank you so much, Jim. It's always nice to come down here and visit all of you here. In my group, we've been thinking a lot about audiovisual storytelling and storytelling tools. And so what I wanted to do today was to tell you about some of the work that we've been doing in this space. But before I start, I just want to take a moment to say that the work that I'll present today wasn't done by me alone. I've been very fortunate to work with a number of fantastic collaborators, including a number of really amazing graduate students. And you see their names at the bottom of this slide. They are the ones who did the heavy lifting on the work that I'll show you today. So I think that the combination of this device with websites like Facebook and YouTube have fundamentally changed the way that we capture and share audiovisual stories. So today, the very best stories can be viewed billions of times. I think this video just crossed the 2.5 billion views mark, which is a pretty astounding number when you think about it. But creating these kinds of high-quality visual stories requires paying very careful attention to story design, to editing, and to production. And it's not just for entertainment, of course. This TED video was posted in September of 2013, and in just over a month, it was seen over 300,000 times. Here again, the people that created the video very carefully designed the content, but also the editing and the production to tell the story effectively. But of course, most internet videos don't look like these. Most internet videos, they contain cats, as we learned recently, and they look more like this. So this is two sisters telling the story of finding this cat. And the video does contain a few nice moments, interactions between the sisters and the cat. But there's also a lot of mumbling and awkward noises as the girls figure out exactly what they want to say. And at almost 3 minutes in length, this video just feels really, really long. It could benefit from some editing. And so the question is why? Why don't people edit their videos? Well, I think a big reason is that today's video editing tools look like this. And I don't know about you, but I find this kind of interface to be really intimidating. Now, in fact, I'll argue later that the problem isn't the surface complexity of these tools, it's that the interfaces use the wrong underlying representation. They force users to work at the frame level and concentrate on the frame level details rather than on putting together the overall story. And so most users just don't take the effort to learn to use these tools. And so I think this is leading to a challenge. The statistics suggest that people really want to create and share audiovisual stories. But as we've seen, the raw media itself rarely tells an effective story. Most of the media isn't that compelling in its raw form. Often it's just too long. On the other hand, the best stories are very carefully planned out, edited, and produced. Yet the current editing tools are really, really difficult to use. And so what I think we need are higher level tools for creating these kinds of audio-visual stories. Tools that allow the storyteller to focus on constructing the overall narrative, or what Vonnegut calls the overall shape of the story. And meanwhile, the computer should handle the lower level details of kind of putting the story together. So I'd like to show you some of the approaches we've developed to build these kinds of tools. And the first approach is to analyze the content of the raw media itself to find semantically meaningful features and then allow users to edit the media using these features. And I'll show you how we've applied this approach in two domains. First on editing interview videos, and second on editing audio stories. And the second approach is to build tools that leverage existing skills, like drawing. People from a very, very young age learn to draw. And here I'll show you a project on creating animated stories via a form of puppetry. So the first project is on editing interview video, or talking head style video. And this kind of video is really common. We see it all the time in things like broadcast news. We see it in talk shows, promotional videos, and documentaries. So these are videos in which a person is just kind of talking to a camera, and it is really, really common. Now, editing this kind of interview footage is very challenging. The raw footage often contains hours and hours of material that has to be edited down to just a few minutes of material. So that can be very time-consuming. And in our work, we often start by examining current practice. So the question here is, how do people edit videos today? And it turns out that there are three main steps. So first, an editor starts by building an index, transcribing the speech and marking the associated times. Sometimes this is called a log. And the index makes it really easy to find specific content later on. But as you can imagine, building this index is extremely time-consuming. Next, the editor has to find good places to place cuts. Places where the speaker is not in the middle of a gesture, not in the middle of saying a word. For example, the cut I'll show you in a second breaks the visual flow of the video because it occurs in the middle of a hand gesture. So watch the hands here.
Now you'll be able to have much more creative layouts. The text will be able to flow across all of those regions.
So finding good cut locations often requires looking at the video frame by frame to finding exactly the right moment to cut. And finally, the editor has to insert a transition that connects the remaining video segments. And visible transitions like fades, jumps, and zooms are most common. They also have well-established meanings. So a fade, for example, often implies a passage of time. In some cases, however, an editor might not want a strong visible break and would prefer to simply transition smoothly between the segments. And interpolation is one technique for creating such hidden transitions. But in most cases, simple optical flow fails because the end frames are not similar enough, as we see in this case with the hands. So all three of these steps are problematic. And our work is going to address all three of them. But the first two problems are especially tedious. And I think that the underlying cause is that current interfaces use a frame-based representation. So users have to index the video and find good cut locations by repeatedly scrubbing back and forth through the timeline to find exactly the content that they want or the place to cut. Yet most people don't think about video, interview video in particular, in terms of frames or time code. They think of these videos in terms of the video content itself, the words, the sentences, and the paragraphs that are being spoken. And so our goal is to let users navigate and edit these videos using a transcript-based representation. So here's our interface. And as you can see, it has three main windows: a standard video player, a kind of standard timeline view, and this new transcript view on the right. The transcript is aligned with the video, which makes it easy to find and play back footage that corresponds, in this case, to the highlighted text.
So what we're trying to do is to bring to our customer the tools that will allow them to express.
So these are really in tight alignment with one another. Now, our transcript view actually looks like this. It marks ums and repeated words in red. And it also has these vertical blue bars. And these bars indicate places where the system thinks it can produce a smooth, high-quality hidden transition if the user cuts between those two bars. And I'll explain exactly what that means in a moment. But the main idea here is that we have a visualization that makes it much, much faster and easier to figure out where you want to make the cuts and the content that you want to delete. You can do all of this by reading the text rather than having to scrub through this timeline. So here, the editor can now apply cut, copy, paste on the text to edit the video. We just remove that phrase, we generate a hidden transition, and I'll show you the kind of smooth result we're able to generate. Pay attention to the hands, okay? The hands should look very smooth in this case.
Of making a story. And
okay, they move on and off the screen fairly smoothly. Just to show you, here's a jump cut. And you saw that jump right at the end. And again, for comparison, here's our smooth transition.
Making a story. And
all right, that one went by fast. I'm going to show a bunch more of these as the talk goes on. All right, so our interface is based on three main algorithmic components. One for building this transcript-based index, one for computing those vertical blue bars, we call them cut suitability bars, and one for computing the hidden transitions between the frames. And I'm just going to briefly touch on all three of these. So to build the index, we start with the raw video footage, and we obtain a verbatim transcript using the crowdsourcing service rev.com. This is an off-the-shelf service. You give it a video, it gives you back the transcript. It costs about $1 a minute, and it includes all of the uhs, the ums, the stutters, and the speech. It's a verbatim transcript. It's really pretty amazing. So we found that these crowdsourced transcripts are far more accurate than current automatic speech-to-text algorithms. Of course, in the future, you might want to replace this with automatic speech-to-text, but this is what we're using today. Now, to align the transcript to the video, we use an audio model of the phonemes, as well as a model of the pauses and breaths. And we then apply a forced alignment algorithm based on an underlying hidden Markov model. And that produces the aligned transcript view that I showed you earlier. So next, we compute these cut suitability scores.
How does
Yeah.
this, I mean, like in YouTube, I've done this many times. You have a transcript, and
Yeah.
you say align it, and it works pretty well. Like,
Yeah.
is there anything new that you're doing relative to that, or what's?
Yeah, okay, so good question. so YouTube is using,
Question.
say again?
Repeat the question.
Yes, good. The question is, are we doing anything beyond what YouTube does with their transcripts for
Well,
their
if you upload
videos?
the transcript, if you just make them do text, speech to text,
Yeah.
they're going to have problems with it. But if you give it a transcript, it will align it pretty well,
Yeah.
in my experience.
Yeah. So we're pretty much using off-the-shelf techniques to do this alignment between the transcript and the underlying audio. Okay? And I assume that's what YouTube is using as well, some technique like this. The main thing that we've added is this model of pauses and breaths. And you'll see later on in the talk that that's really important for certain kinds of edits. To make speech sound natural, it's important that you maintain the breaths and natural sounding pauses. So we'll get back to that. But we're not really doing too much new here. Yeah. Any other questions? Okay. So the next step is computing these cut suitability scores, and we're going to use these scores to place the vertical blue bars that indicate places where a cut is likely to lead to a smooth hidden transition. And remember, editors prefer to place cuts where the speaker is not gesturing and not in the middle of speaking. So to identify such potential cut locations, we assign a cut suitability score to each frame that combines a visual score and an audio score. For the visual score, we first compute a visual distance between the frames, and this distance includes a spatial component as well as an appearance component. So for the spatial component, we first run Saragi's face tracker to obtain facial landmark points on each frame. And these mark the eyes, the nose, the mouth, and the face contour. And then we set the spatial distance to the distance between the centroids of these landmark points. So it's kind of just a coarse spatial representation of where the faces are in the frame. For the appearance distance, we compute a histogram of oriented gradients, or hog features, around the eyes and mouth of the speaker. And we also use the position of the head to estimate the position of the body, and we compute hog features in this region as well. And these body features are really crucial for our application because they capture the hand gestures that usually appear in front of the body. So we need to capture the variance in appearance in that region. And so the distance then is proportional to the normalized chi-square distance for these feature vectors. And we now combine these into a full score. We convert this appearance distance into a cut suitability score by comparing each frame of the raw footage to a reference frame where we know that this speaker is not gesturing and not speaking. So video producers often capture this kind of a reference frame at the beginning of the raw footage where the speaker is simply listening to an off-camera interviewer. So there often is this kind of frame in a known location, and we can easily get to it. We set the we set the visual score here so that the score is high when the distance to the reference is low. So for the audio score, we rely on the alignment between the text transcript and the speech and set the score to 1 whenever the speaker is between words, as shown here. And then we combine the visual and audio score and threshold the result to generate the blue bars in this transcript view. Okay, so fairly straightforward. And finally, our system can generate smooth hidden transitions. So our goal is to take a jump cut that looks like this.
Public space
and turn it into a smooth transition like this.
A public space that is rendered out.
So one way to compute this kind of transition is to build a complete graph in which each node is a frame and edge weights encode the frame distance that I showed you earlier. Given the start and end frames of a cut, we can then apply Dijkstra's shortest path algorithm to find the smoothest set of in-between frames in our video. The problem, of course, is that building this complete graph has order n squared complexity. And with raw footage that has tens of thousands of frames, this approach quickly becomes intractable. So instead, we're going to start by clustering the raw frames hierarchically using a greedy algorithm. We start by building the top-level clusters, and then further subdividing each cluster until we reach the individual frames. And then to approximate the shortest path, we work in a top-down manner again. We start with the top-level cluster centers and build a matrix of pairwise distances between them. We then find the shortest path, and in this case it goes from C1 to C2 and then C4. And then we're going to refine our distance matrix by first adding the orange edges between subclusters, and then adding the cross-cluster gray edges. And these refinements all ensure that when we compute the shortest path at this level, it'll follow the sequence of clusters that we computed at the higher level. And we repeat this process all the way down to the leaves, and that produces our shortest path. Now, I should point out that in the worst case, this is still an order n squared algorithm. But in practice, this approach really exploits the coherence in the videos. And what we've observed is that it runs much, much faster than order n squared. In many cases, it scales linearly in the number of frames. OK, so here again is the cut for which we wanted to generate a hidden transition.
A public space that is rendered out.
And when we insert the in-between frames from our path, we obtain the following video.
A public space that is rendered out.
So the transition here appears smoother, but the woman's head motion is too fast during the transition compared to the rest of the clip. Right? It looks odd. So we need to fix the timing of the transition. Given these two n frames, the shortest path algorithm provides these in-between frames. And we can slow down the transition by inserting additional frames between any pair of frames on this path. Right? And we can determine those frames using the simple optical flow approach that I showed you earlier. But because these frames are so close to one another now, optical flow can work in these instances. So the question then is, how many of these in-between frames should we add? Should we add 1 frame, 2 frames, 3 frames, 4 frames? How many should we add so that the motion has the right speed? It looks natural. Well, we're going to take a data-driven approach to figure out the number of in-between frames. The way we do this is we start with our raw footage, and we consider pairs of frames I and j, and we build a histogram that relates n, the number of intermediate frames between I and j, and d, the frame distance between I and j. All right, so we get this two-dimensional histogram. Then for adjacent frames on our shortest path, we compute the frame distance between them and look up the corresponding row in the histogram. And then we set n to the bin containing the maximum value. All right? So we're using the data that we have in all of the raw footage to figure out the in-between frames and also the number of additional interpolated frames we should add. And here's the resulting transition.
A public space that is rendered out.
Okay. So I want to show you some more results. This is first with jump cuts.
Profoundly disturbing. I had a phone call from my daughter who said that she
she didn't know whether the house was standing.
Okay, and I should point out that I didn't talk about it, but the same algorithm we use to generate hidden transitions can also be used to insert natural-looking pauses into the video. So you'll see an example of that here.
It was profoundly disturbing. I got a phone call from my daughter, who said that she didn't know whether the house was standing.
Here's another example.
So a course was fixed and a start was made. The hare darted out of sight at once, but soon stopped. To show his contempt for the tortoise, lay down to have a nap. Tortoise plodded on and plodded on.
Here's our result.
You should both stay until you have eaten, said the tortoise. Shall we race? So a course was fixed and a start was made. The hare darted out of sight at once, but soon stopped. And to show his contempt for the tortoise, lay down to have a nap. Tortoise plodded on and plodded on.
Okay, one more.
Eighth and ninth grade, and the basic idea that motivated this exhibit was earth, air, eighth and ninth grade, and the basic idea that motivated this exhibit was earth, air.
Okay, so that's what our system can do. Now, I should point out that there are, of course, limitations to this work. Here, our system has to transition from a frame in which the hands are not visible to one in which they are visible. So the hierarchical graph that we constructed doesn't contain a smooth path to bridge this cut, and we get this funny-looking result. Our approach also depends on some assumptions about the background, the lighting, and the camera position, in particular that all of these are fixed. And so there is some future work to relaxing these assumptions. Now, in building this kind of a tool, I think it's also really important to evaluate them with the target users. And so we showed our interface to 9 professionals, video editors, and working journalists from the Berkeley School of Journalism. And their feedback overall was very positive. They thought that the system would fit well into their existing workflows, which indicates to us that they could easily adopt the approach. And they also really, really liked the transcript view. They thought it would be very useful for navigation and for editing. And that was the one piece of the system that they wanted right away. Finally, they thought that hidden transitions would provide a new useful alternative to visible transitions. But they also noted that the hidden transitions would be best for online videos. At higher resolutions, you might have seen it, there's still a little bit of blurriness that's introduced by our technique. And so there again, I think some additional work is really necessary. So to me, the overall takeaway from this project is that choosing the right representation can make an interface significantly easier to use. And how do we choose this right representation? Well, we should pick the one that matches the user's conceptual model of the content. For interview videos, the transcript representation better matches the way people think about such videos compared to the standard timeline-based representation. And I think that this relates to what cognitive psychologist Barbara Tversky calls the principle of congruence. So she says that for effective interfaces, the structure of the external representation used by the interface should match the structure of the user's mental representation. And she originally stated this in the context of visualization, but I think it relates to earlier ideas that were really invented here by Don Norman and Jim Holland and Ed Hutchins, where they said that interfaces in which a systems model matches a user's conceptual model really reduces the gulfs of execution and evaluation. So one open question here is, what is the appropriate representation for other types of video? Here we've really focused on interview videos, where a lot of the content is carried by the speech. How do people mentally think about videos that focus less on speech and more on visual actions, like sports videos or cooking videos or videos in other domains? And I think this is really an important question for future work. And one of the directions I'd like to go in going forward. Okay, so I want to switch over to the next project. Are there any questions about this one? Yeah.
There's one question. When we played with slowing down, speeding up video, for example, like to conduct an orchestra, we quickly realized that it's very hard to do that and still make it look natural, because there are things happening in a video that actually happen at different natural speeds. For example, if a violinist slows down his play, the arm slows down, but he still blinks at the same frequency and speed, and his frock, will still wave back and forth at the same time. So it often looks like people are being like sort of suspended in zero gravity when you do slowdowns, or they look tired because their eyes close and open more slowly.
Right.
So, and here, especially with the interviews, you're really looking at a person's face quite directly, and I'm wondering whether you saw any effects of things starting to look unnatural, and especially whether you took any steps towards sort of avoiding those sort of zombie effects that sort of look weird because somebody's not, muscles aren't working in the natural speeding way.
Yeah. So we didn't take anything beyond what I showed you, any measures beyond what I showed you. The question was, did we do anything additional to address the fact that we might introduce unnatural motions or unnatural frequencies or timing of the motions? The goal of our interpolation, that piece of it, was to kind of match the natural motions and frequencies of the speakers. And we did that in a data-driven way. And that produced pretty good results. But if you look closely at our results, there still are some unnatural head motions. And I think that's partially what the journalists were complaining about when they said that this would be best for small web videos. I think there is some work that still needs to be done to address the issue that you're bringing up. Right, but for quick one-offs, this kind of thing might work pretty well. Okay. All right. So beyond interview video, another very powerful medium for storytelling is audio. And we've recently developed tools for editing and producing audio stories. And these stories are commonly heard on radio shows, in audiobooks, and on podcasts. And I have long been interested in the way that these kinds of stories use editing and production techniques to really deeply engage listeners. In fact, I spent my last sabbatical working with producers at Studio 360 in a public radio program at WNYC in New York to better understand the techniques that they use to tell and create compelling stories. And for me, I have to say, this was a fantastic learning experience. I just kind of threw myself into something I knew very, very little about, and it was great to spend a lot of time learning from ground zero again. I really think it's a great way to spend a sabbatical. Along the way, while I was working with them, I also found some published resources, like this book from the creators of This American Life, and websites that describe design principles for effective audio storytelling. And these are editing and production techniques that the producers use to emphasize the mood, emotion, or narrative structure of a story. For instance, think about how the musical score serves to highlight the speech in this example.
I ran down a list of recent crimes, looking for a conviction that might stick. Setting fire to a reportedly flame-proof Halloween costume. stealing a set of barbecue tongs from an unguarded patio, altering the word hit on a list of rules posted on the gymnasium door. Never did it occur to me that I might be innocent. You might want to take your books with you, the teacher said, and your jacket. You probably won't be back before the bell rings.
So what are the steps and principles involved in adding such a musical score, a musical underlay to the story? Well, the first step is to select a point in the speech that we wish to emphasize. So here, I'm going to choose the word, the point right after the word innocent, because it marks an important change in the overall mood of the story.
Never did it occur to me that I might be innocent.
Next,
you might want to take your books with you, the teacher said.
Next, we consider the music, and to highlight the emotion in the speech, we have to find an exciting change point in the music. Here, the music is going to start with some rhythm, and there's going to be a change point when the keyboard comes in. The third step is designed to give the listener some time to reflect on what was just said. So we're going to separate the speech at the emphasis point and align the music change point to play just after the speech pauses. And finally, we adjust the volume of the music to start low and crescendo at the change point, play at full volume during the gap, and then fade down.
Setting fire to a reportedly flame-proof Halloween costume. Stealing a set of barbecue tongs from an unguarded patio. Altering the word hit on a list of rules posted on the gymnasium door. Never did it occur to me that I might be innocent. You might want to take your books with you, the teacher said. And your jacket. You probably won't be back before the bell rings.
So each one of these 4 steps is really time-consuming and requires a fair amount of production design skill to get it right. And so we've built a set of tools that are designed to facilitate all 4 of these steps. I don't have time here to talk about all 4 of them, so I'm just going to focus on step 2, finding this music change point. Now, music change points are usually characterized by strong changes in tempo, in dynamics, instrumentation, or harmonic content. And often the producer has to listen to the entire song multiple times in order to find these change points. So again, this is a lot of scrubbing back and forth through the timeline. And it's a time-consuming process. Now, fortunately, computer music researchers have developed signal processing techniques that can help us algorithmically find such change points. And they've developed features that correspond to changes in tempo, dynamics, instrumentation, and so on. And so we're going to use a multi-scale approach to compute the maximum differences in these features, first at a coarse scale and then at a fine scale. And our algorithm will return the top 3 strongest change points. So algorithmically, we're finding where these things are, and the user can then use them. So this is what our interface looks like. And I'll just walk you through the process of adding a musical underlay. So first, I'm going to choose a speech track. Here, I'm going to choose a reading of Great Expectations. And I'm going to mark an emphasis point in this speech. I'm then going to select a music track. In this case, I select the track Tenuous Gears by the band Damiac. And I then press this Automate Underlay button to generate the underlay. And the system finds the strongest change point in the music, aligns the music and the speech, and adjusts the volume, as I showed you earlier. And now I can listen to the result, and I can press the next button to generate an underlay for the next strongest change point in the music. So this tool removes a lot of the low-level work required to make an underlay, and I can very quickly test different change points in the music, or different pieces of music, until I find the best one that I like. So this tool is really designed to facilitate iteration, and as we know, the more we iterate, the more likely it is we will converge on a design that is really effective. So let's listen to this result.
Gave up trying to get a living exceedingly early in that universal struggle. I am indebted for a belief I religiously entertained, that they had all been born on their backs with their hands in their trouser pockets, and had never taken them out in this state of existence. Ours was the marshy country down by the river. Within, as the river wound, 20 miles of the sea.
Okay, here's another example. I'm going to go back to David Sedaris, but a different piece of music.
Setting fire to a reportedly flame-proof Halloween costume. Stealing a set of barbecue tongs from an unguarded patio. Altering the word "hit" on a list of rules posted on the gymnasium door. Never did it occur to me that I might be innocent. You might want to take your books with you, the teacher said, and your jacket. You probably won't be back before the bell rings.
Okay, and in this next example, I'm going to stick to Sedaris, but I'm going to change the music to a very different track just to show you how different music completely alters the mood.
Setting fire to a reportedly flame-proof Halloween costume. Stealing a set of barbecue tongs from an unguarded patio. Altering the word "hit" on a list of rules posted on the gymnasium door. Never did it occur to me that I might be innocent. You might want to take your books with you, the teacher said, and your jacket. You probably won't be back before the bell rings.
So to evaluate these results, we asked 3 people, avid radio listeners, to rate each of the 26 underlays that we generated using this tool. And they evaluated the timing, the dynamics, as well as the overall satisfaction. And we found that they were overall satisfied with about 86% of our results. So this is some indication that the tool is working. And we were very happy with that. Recently, we've combined this project with the transcript-based editing approach that I showed you earlier. So here's the interface for the new project. This is all about editing audio. And this is the raw speech for an audio story that appeared on Studio 360.
Okay. He's not just a fan. Whenever Bullwinkle makes an appearance these days, that's Keith Scott on it. Ugh. He's not just a fan.
So in this case, our transcript view shows all of the text as well as tokens for pauses and breaths. And this is where breaths and pauses become really important to make it sound right for the radio. As you can see, there are also a lot of kind of mistakes and errors in that raw speech, and we want to be able to edit those really, really easily and quickly. So we can do the kind of cut, copy, paste that I showed you earlier, but we also incorporate additional design principles. So first, it's really important for speech to sound natural after you do an edit. And so we provide this tool for inserting breaths and pauses between the edits to make it sound correct. Second, in the raw footage, the speaker will often try out different phrasings or voicings of a line. And so we provide a tool that finds all of these repeated takes and groups them together to make it easy to listen to the different versions and select the best one. And finally, our tool can recompose the music track to smoothly align multiple change points with multiple emphasis points in the speech. And so here we're adding or removing loops automatically in the music. So here's an editing session. I start by cutting out some of the speech, some of the mistakes. I then consider several different voicings of a line and choose one. I edit some more. Then I add in an emphasis point, a second emphasis point, and then I ask the system to compose the score.
He's not just a fan. Whenever Bullwinkle makes an appearance these days, that's Keith's stop behind the antlers. And unofficially, he's the closest thing to a Bullwinkle historian. In episode 1, Bullwinkle sets off an international incident, and the pie he's making turns out to be the recipe for a super powerful jet fuel, which naturally attracts the attention of super spy Boris Badenov. In real life, the doomsday clock.
Okay, so that gives you a sense of what we're able to do. Now, I want to take a step back and focus on the methodology we used in these audio stories projects. We started by identifying design principles for effective audio stories, and we did this by observation as well as by looking at prior publications about how to create effective stories. We then instantiated these design principles into algorithmic tools and techniques, and this step required translating high-level design principles that were written for other humans to follow and translating them into a sequence of lower level operations and algorithms that a machine could implement. And finally, we started to validate some of the results through user feedback. And a few years ago, this is a methodology that I've been using all the way from the time I did my PhD thesis on maps, as Jim mentioned at the beginning. So we've used it in a number of projects, and a few years ago, we wrote an article describing this methodology in detail and various applications of it from our work. And I just want to point out that there are many, many other design domains in which this methodology, I think, can be applied. And this, again, is something that I'm excited about continuing to apply in different domains. OK, I want to end here by talking about a very different storytelling tool. Well, somewhat different, let's say. A few years ago, I got interested in helping users create animated stories. So far we've been talking about video and audio. Now I want to consider animation. And I was especially interested in building tools that even young kids could easily use with very, very little training. Ideally, just walk up and use. And the problem is that most existing animation software is inaccessible even to adults. This is Adobe Flash. It is complicated. But here again, I think the problem is the underlying timeline-based representation. Users have to specify motions by setting keyframes. Most people don't think of motions in terms of keyframes. They think of motions in terms of the movements. Even kids regularly act out stories by moving around. And so we created a tool that lets kids animate by moving around paper characters. Users draw the characters on paper. They then cut them out and show them to an overhead camera. And our system mats out the characters. Then, as the user moves the physical paper puppet, our system tracks the character in real time, and it re-renders the matted version onto a new background with the hands removed. So that's all there really is to it. Just to give you a sense of the technology here, the key thing that we need to make the system work are the abilities to identify and track the puppets. SIFT is a very well-known feature detection technique that can identify the puppets. Here it can distinguish between the sun and the moon. It can also locate or track the puppets within the frame, but when we implemented our system at that time, SIFT didn't really run in real time, and so here you can see that there's a kind of lag in the tracking. KLT is an optical flow-based tracker that can locate the puppets in real time, but it can't distinguish between them. It can't identify the sun and the moon. And so our approach is to combine these two algorithms to identify and track the puppets in real time. And we can then retrieve the corresponding puppet mat from our database and render it onto a new background to generate the animation that you see here. So that's the basic approach. Our system can also handle articulated characters. And notice here that the physical puppets don't have to be attached to one another. And this can make it a lot easier to control the puppets. So here again, we start with a picture of each puppet part, and then mat the parts out. And then we require the user to do a little bit more work with an interface that we built to specify how the parts are connected. Okay? So we're losing a little bit of that walk up and use ease of use, but we're gaining the ability to do articulated characters. And there's a kind of trade-off there that I think we're still exploring. Okay, here's an animation that was created by an 11-year-old user. He did all of the work to make this happen. And notice that fire special effect, which burns the knight who then gets eaten by the dinosaur. Invoking the fire required an additional bit of interface to attach this fire puppet to the pre-built fire effect. Okay? So once again, we're adding a bit of complexity to our interface, and there's a trade-off here. And you know, it's a very simple piece of interface, but nevertheless, you need to use something like this. Okay, we can change the backgrounds by showing a different picture to the system, and we can pan and zoom the camera by moving the hands, as you see here. We can also introduce layered 2.5D environments and walk cycles for the characters. So here, again, we have to add more interface. So here, you can specify the swing rates for the arms and legs. And for 2.5D, we have to specify a horizon line, and that sets up a ground plane for us. And we can also scale the character as he moves upwards in the image plane to give this perspective effect.
Our final effect uses peaks in an audio stream to trigger the advancement of a flip-up animation of a character's mouth. In summary, our system provides a simple interface whereby people of all skill levels can create cutout-style animations by manipulating puppets.
So that's the system. And we took this puppetry system to the Maker Faire in the Bay Area in 2008, and the real-world deployment was incredibly instructive to us. We had hundreds of people come through and check out the system, and children as young as 4 years old were able to draw the characters and animate them. So that was really great. We also made a few observations. So first, real-time feedback is very, very useful. It allows users to quickly test different story ideas, and again, we get this kind of fast design iteration. And second, we saw that people performed the same motions multiple times before they were satisfied. And this implies that a tool for refining and editing the motions could further help users. And that's one kind of direction for future work. Okay, we've recently extended our approach to work for 3D toys using a Kinect camera. So here you can see the system working. And here's a result we created. Okay, and one more.
How did you go from the toy to the model on the computer? Was it did the 3D mapping itself, or those models that are supposed to be already in the system?
We scanned them as an initial step. We scanned them, just like we created the puppet mats in 2D by taking a picture and automatically matting out the puppets. In 3D, we use the Kinect camera to scan those objects, the toys, and then we have them in a database and we can animate them. All right, so what I've shown you are storytelling tools that allow the storyteller to focus on building the narrative, while the computer handles some of the lower level details in managing the media and putting the story together. And I think this work is built on two key ideas. First, storytelling interfaces should use representations that match the user's conceptual model as much as possible. And this makes it easier for users to express the overall story design, and it can decrease interface complexity. And as in the puppetry system, it can also allow users to apply their existing skills and knowledge. And second, storytelling tools should incorporate design principles. And this approach lets novice users really leverage the design knowledge of experts. So that's where I'd like to end. But before I finish, I'd just like to again thank all of the people that made the work possible. These are the students that are the first authors on the papers that I showed you. They are the ones responsible for the work. For more information about these projects, you can check out our website. And I should also mention that the code for the 3D puppetry project that I showed you at the end, that is available. So, download it, compile it, run it. It does require a bit of work to compile and get running, but if you're interested, please check it out, and we'd be happy to help you with that. Thank you very much.